Now we'll look at the connections to the theoretical sampling distribution and normal model. For inference procedures, we work from a mathematical model of the sampling distribution instead of simulations, but we always begin our discussion with a simulation to highlight the sampling process. Simulations also remind us that the sampling distribution is a probability model because the sampling process is random and we look at long-run patterns. Recall from distribution of sample proportions our discussion of the mathematical model for the sampling distribution of sample proportions. For samples of size n, the model has the following center and spread, both of which are related to the population with a proportion p of successes. The center is the mean of the sample proportions, p, the population proportion. Spread, standard deviation of the sample proportions, also called the standard error, is, we've seen this formula before, the square root of p, which was mentioned above, the mean of the sample proportions, times 1 minus p, all divided by n, the sample size. The shape, a normal model, is a good fit for the sampling distribution if the expected number of successes and failures is at least 10. We can translate these conditions into the formulas. N times p is greater than or equal to 10, and we've seen this before, and n times 1 minus p is greater than or equal to 10. Let's see, I think I kind of covered the n in that formula. You can't really see it. Let's do that again. Oh, geez. Sorry. All right, there we are. If we can use a normal model for the sampling distribution, then the empirical rule applies. Recall the empirical rule from probability and probability distributions, which tells us the percentage of values that fall 1, 2, and 3 standard deviations from the mean in a normal distribution. 68% of the values fall in 1 standard deviation of the mean, 95% of the values fall within 2 standard deviations of the mean, 99.7% of the values fall within 3 standard deviations of the mean. I think we've seen that before. That was the empirical rule, right? Okay. Let's scroll down and see what else we're looking at. When we have a normal model, when we have a normal model for the sampling distribution, the mean of the sampling distribution is the population proportion. These ideas translate into the following statements. 68% of the sample proportions fall within 1 standard error of the population proportion. So just rephrasing what we said above, the empirical rule, 95% of the sample proportions fall within 2 standard within 2 standard errors of the population proportion. 99.7% of the sample proportions fall within 3 standard errors of the population proportion. Therefore, the empirical rule tells us that there is a 95% chance that sample proportions are within 2 standard errors of the population proportion. A margin of error equal to 2 standard errors, then, will produce an interval that contains the population proportion 95% of the time. In other words, we will be right 95% of the time. 5% of the time, the confidence interval will not contain the population proportion, and we will be wrong. We can make similar statements for the other confidence levels, but these are less common in practice. For now, we focus on the 95% confidence level. With the formula for the standard error, we can write a formula for the margin of error and for the 95% confidence interval. So before we saw this one, sample statistic plus or minus the margin of error. So we'll rewrite it as sample proportion plus or minus 2 times the standard error. We saw that on a previous page, but we can write it more as a formula. The sample proportion we write as P with a little hat or a little, I don't know, accent mark, I forget what they called it. And plus or minus 2 times the standard error. But now in this particular example, we're looking at standard error is that formula we saw before. P times 1 minus P over N, all under the square root. Remember that we can make a statement about our confidence that this interval contains the population proportion only when a normal model is a good fit for the sampling distribution of sample proportions. Now let's make a comment. You may realize that the formula for the confidence interval is a bit odd, since our goal in calculating the confidence interval is to estimate the population proportion P, yet the formula requires that we know P. So how can we estimate P, or why would we even want to estimate P if we already know P? For now, we will use an estimate for P from a previous study when calculating the confidence interval. This is not the usual way statisticians estimate the standard error, but it captures the main idea and allows us to practice finding and interpreting confidence intervals. Later, we'll estimate the standard error using p-hats as we did in the previous quiz. Using p-hat to estimate standard error is commonly used in statistical practice. Okay. Now let's look at this example. I think you might have seen an example around this before. Recall the use of data from the National Health Interview Survey conducted by the CDC to estimate the prevalence of certain behaviors such as alcohol consumption, cigarette smoking, and hours of sleep for adults in the United States. In 2005 to 2007, in a report in that time frame, the CDC estimates that 68% of men in the United States are overweight. Suppose we select a random sample of 40 men this year and find that 75% are overweight. Using the estimate from the survey that 68% of the US men are overweight, we calculate the 95% confidence interval and interpret the interval in context. So in the previous pages in this module, we've done a lot of theory, but here's all that theory put into practice in an example that we've seen before. So let's first check normality conditions, because we can only use all these formulas if this is actually a normal distribution. Yes, the conditions are met because the number of expected successes and failures in a sample of 40 are at least 10. We expect 68% of the 40 men to be overweight. So we calculate, remember we said n times p must be greater than or equal to 10. N times p, here they calculated n is 40, that's the sample size. 0.68 is the sample proportion. If you multiply those, it's a little more or a little less than 13. Either way, it's greater than 10. So we can use a normal model to estimate that 95% of the time, a confidence interval with a margin of error equal to 2 standard errors will contain the proportion of overweight men in the United States this year. So calculate the standard error, estimated average amount of error. So we've seen that formula above, right? The square root of p times 1 minus p over n. So p here, they put 0.68 times 1 minus p, 1 minus 0.68, all over n, but the n is the sample size of 40. And they subtracted 1 minus 0.68, they got 0.32 here, as you can see. So you multiply 0.68 by 0.32, whatever you get for that, divide it by 40, whatever you get for that, take the square root, and they get about 0.074. So now we can find the confidence interval. Should be the sample proportion plus or minus the margin of error. Okay, and the sample proportion that we mentioned in that kind of the question they framed here is they said, in a later year or a more recent year, if they found that 75% of men are overweight. So that's the sample proportion we're interested in for this problem. I'm going to bring that down. That's 75% in decimal form is 0.75 plus or minus 2 standard errors. Now 2 times the number we found up here, 2 times 0.74. So 0.75 plus or minus 2 times 0.074. 2 times 0.074 down here is 0.148. So I'm taking 0.75, the number on the left, and in one case, subtracting 0.148. When I subtract, I get this number, 0.602. When I add them, 0.75 plus, sorry, let me erase a little bit so it's not so muddied, I guess. Is that a word? I don't know. Sounds like a word. 0.75 plus 0.148. That's how they get this larger number here. Okay, so from 0.602 to 0.898, that's our confidence interval. Okay, now let's think about interpreting that. Okay, so our interpretation is that we are 95% confident that between 60.2% and 89.8% of US men are overweight this year. Because that was our confidence interval, just kind of translating those decimals into percentages.